The Mars Curiosity probe is down on the surface of the red planet and doing marvelous work already.
Curiosity is NASA's latest mission to Mars. It's taken years to develop, and it's the most advanced vehicle ever to be sent to another planet. This is NASA putting it through its paces in the lab, and you can see how big it is. It's the size of a Mini, but it weighs over a ton. Thanks to a small nuclear power source, it should have enough oomph to climb a Martian mountain. On board are a fleet of amazing instruments. These test shots show the movable arm with its cameras and its spectrometers, which will be used to examine rocks. And it's got a laser which will zap rocks, telling the scientists if the rocks are interesting without all the hassle of driving up to each one. If they do turn out to be interesting, and I'm sure some of them will, Curiosity can test samples with its ovens and with its onboard chemical laboratory.
Fire.
But its size and its weight mean that Curiosity needed something really rather special to reach the surface.
Liftoff of the Atlas V with Curiosity.
Curiosity, then known as Mars Science Laboratory, was launched last November. And in early August, finally arrived at the top of the Martian atmosphere. With us to discuss Curiosity from University College London, Dr. Peter Grindrod, and of course Chris North. And Chris, it's been a really exciting couple of weeks.
It's been incredibly exciting. I mean, it all started for us early in the morning, on that morning, the 6th of August here, when Curiosity landed. An incredibly exciting event, because the landing was just so exciting. I mean, with everything that's going on, it had a sky crane and thrusters and a parachute and all these things to make the landing incredibly exciting.
The dreadful 7 minutes.
Yeah, the 7 minutes of terror, they called it, where for 7 minutes there was nothing they could do. It was running on its own. It's 14 light minutes away on Mars, so it took 14 minutes for any signals to get back. Absolutely nothing that could be done. And its target was Gale Crater on the surface, but it was an incredibly exciting journey down.
Pete, can you start talking us through what had to happen to get it safely onto the ground?
Yeah, sure. There are a number of things that had to happen. The first is to enter the atmosphere at the right point so that the heat shield could slow the craft down enough to slow it down from 13,000 miles an hour down to, about 1,000 miles an hour by the time the atmosphere had done its job, and at which point the parachute could then come out for the first time.
Parachute deployed. We are decelerating.
And the heat shield's ejected, and we actually had some amazing pictures of the heat shield. We got them later, not live. But the heat shield falling down across the Martian surface. It's quite remarkable to be able to see this in a descent.
We're down to 90 meters per second at an altitude of 6.5 kilometers and descending.
We even got a photo of Curiosity on its parachute.
From the Mars Reconnaissance Orbiter. And it's great to be able to see this, to have a spacecraft taking a picture of another spacecraft descending, but that wasn't the hard bit. What happened next?
Curiosity dropped down away from its back shell and parachute.
We are in powered flight.
And then moved away from the parachute and left it behind, and then started to descend on its own powered rockets then. So coming down, kind of 8 thrusters controlled it, slowed it down, make sure it was all smooth. It slows down to an almost kind of stop, hovering above the surface.
Sky crane has started.
So about 20 meters above the surface, then Curiosity, the rover part, then descended on its own kind of cables on this sky crane technology. This was the part that we'd never seen anything like this before.
You're stable.
Patrick, I don't know what you thought, but this looked completely insane to me.
I thought, this is not going to work.
UHF is good. Touchdown confirmed. We're safe on Mars.
Chris, why did they have to do this? Previous rovers had bounced to a stop, so why have this complicated sky crane?
Curiosity is the size of a small car.
Too heavy.
Yeah, it's too heavy. It weighs a ton. That's far too heavy to bounce down on airbags, which is what previous rovers have done. The other problem is that it had to come down on these thrusters, but you don't want the thing to land on thrusters. You want it to land on wheels, so it couldn't have the thrusters on the rover itself. And besides, that's dead weight you've got to drive around. So once it's landed on the surface, this sky crane, this jetpack, if you like, has done its job and gets sent off to go and crash elsewhere on the surface, a few hundred meters away.
Well, out of the way.
Word came back that it was safely down, and then almost immediately we got the first images coming back. You could see that Curiosity was on a flat surface, it wasn't tilted, it looked safe, And then even straight away you can start to see some things in the distance.
Well, let's talk about the landscape, Patrick. You've covered more Mars landings than anyone else. What does Gale Crater look like to you? How does it compare to where we've been before?
Well, rather the same. Flattish, and all covered with red powdery stuff.
The sky pink, of course, which is now familiar, and rocks in the foreground as well.
Yeah, there aren't too many big rocks, but of course this landing site was chosen because there were few rocks there, because it's safest to go where there are no big boulders that could damage the rover. So that's not too much of a surprise. The thing that's affected me is the view. This is a view across the plain of Gale Crater, the floor of Gale Crater, which is very flat, looking towards the raised rim. It's about 2 kilometres high, the rim at this point, and it's quite eroded, so it's not a sharp crater rim, and it's a bit kind of hazy because there's dust in the atmosphere before we get there. But to me, it does look like Mars, but there's a kind of earthliness about this image. It looks familiar when you look at this image. You recognise features.
Is this Mars or Earth? Have we made some ghastly mistake?
Oh, it's definitely Mars. Definitely Mars.
So that's why we needed that Mars Reconnaissance Orbiter shot of it on the way down.
I think one of the surprising things about this image is actually the scale. So the crater rim that we're seeing in that image there is something like 50 kilometres away. It's quite a long way in the distance. As Pete said, it's 2 kilometres high. It's a big rim. It's the same area as Wales, to use a normal unit of measurement in areas. So it is a big place. And the other images we've got besides the rim, of course, are the central mountain.
This mountain in the centre, which is the reason we're at Gale.
Mount Sharp.
Mount Sharp. And it's a big one, right? What is it, 3 kilometres from base to
It's
top?
bigger, about 5.
So on Earth, that's like Kilimanjaro size, something like that.
It's
So this
massive, yeah.
Well, Mount Sharp is distinctive, but why choose that for this particular landing?
The reason that Mount Sharp's interesting is because it's 5 kilometres of rock, but more than that, it's layered rock. And these layers are almost like a timeline, a history of events, of the environments that have existed on Mars. And basically, the further down you go in this mountain towards the base, the further back in time we hope we can actually analyse. And the chemistry from orbit seems to suggest that down near the bottom of the mound, near the bottom of the layers, there was some kind of water around interacting with the rock and altering it to give it a different chemistry. Then as you move up the mound towards the middle, it starts to dry out. And even before then, the chemistry of the water might actually change as well. And then it dries out towards the top, where the top of the mound looks like it's probably always been dry up there. So this is not only a timeline of rocks forming, throughout Martian history, but also recording the environmental change that seems to have happened in Gale Crater.
So we go from a watery environment to one with maybe acidic water around. We've seen evidence for that elsewhere on Mars with Spirit and Opportunity, and then up to the dry present. That's the rough sequence we're after.
A good point here, the Gale Crater is fairly typical of many Martian craters.
Yeah. Before we talk a bit more about that, why don't we look at the rover itself? Chris, what's it been doing since it landed?
So it landed at the start of August. The first thing it did was take some photos just to check where it is. It's got a mast that shortly after landing it had to deploy, so this mast had to lift up. And the mast is able to take a 360-degree panorama by spinning round. The rover is got 6 wheels, and all of them can be driven independently to give it full flexibility. But of course, one of the things it did a couple of weeks after landing was to actually drive a short way just to check that the wheels worked. It drove a few metres and did a little loop-the-loop.
One thing I noticed that was very odd, but predictable, when you look at those photos showing the wheel tracks, they appear to start in the middle of nowhere, which feels very, very strange.
It's almost like it just dropped out the sky.
Well, it did, exactly, or was lowered out of the sky. So why is the arm important? What role does that play in the mission?
Well, it's a 2-metre-long arm. It's got this turret on the end that weighs 30 kilograms. That's more than the payload on some other missions to Mars in the past. And that arm can not only analyse the rocks up close with a hand lens, a magnifier, and a spectrometer as well, but it can also take samples from the ground. It can take a dust sample, or it can actually drill into a rock, take some of the material off the rock from inside it, and then bring the sample back onto the body of the rover.
Yes, and of course we have some ovens on board.
Yes, and there's two main instruments. One is an X-ray instrument that will look at the minerals inside the rocks, and the other one is a set of ovens that will heat up the sample to really high temperatures and analyse what's given off during that process, and from that understand the kind of the organic makeup of the samples.
But you can't put much material in each one. We're talking what? Just a pinch of soil, something
About
like
40 milligrams, think, a very small amount, a pinch of Martian dust or rock into the instruments on board.
Up to now, each probe has done what previous probes have done, but done it better. But this one is entirely new.
It's a league above the rest, right? It's got 10 instruments on board.
I think the one that's got the most attention, just because of what it is ChemCam, which comes with a laser, and quite a powerful laser at that. So if you'd like to explain why we put a robot with a laser on Mars, I think that might be good. It sounds like something out of science fiction.
It is, absolutely. I think we do it because we can. It's a great instrument, so it means that rather than having to go up close to a rock to either take a sample or analyse it in situ, you can actually fire this laser from up to about 7 metres away and analyse what the rock is made of. And then that gives you results in itself. You know, the laser vaporises the rock and you can analyse the plasma that's given off. But then if that's really interesting, then actually maybe we want to drive over there, take a sample and analyse it in even more detail on board.
But it means your first step doesn't have to be to go and get a sample.
Absolutely, yes. And it also means we can access rocks that otherwise we wouldn't be able to drive up close to.
I should know the answer to this, but I don't. How long do you expect Curiosity to go on working?
Well, this is why Curiosity is a completely new kind of mission, because it's designed to last for 1 Martian year, which is almost 2 Earth years. It's not in any rush to kind of start driving quickly. It's doing a very thorough checkout of all the systems and instruments first, and the science will slowly pick up over the months and years.
One of the reasons that Curiosity can last for so long is that it's actually got a nuclear generator. This power source will work 24/7, or 24.5/7, because the Martian day is 24.5 hours long. So not only has it got a laser, it's a nuclear-powered laser robot, which is quite fun.
It's pure Doctor Who.
It really is. It really is a nuclear-powered lasered robot. But to come back to the science, it has shot its first rocks.
The first target it shot with a laser was part of the commissioning phase of that instrument and the rover. And it looked like, you know, it kind of seems strange to say this, but like a typical Martian rock. We're used to seeing rocks on Mars now. It looks like it's kind of a typical Martian basalt, a lava basically on the surface.
So a basalt, just like we might have here on Earth.
Yes, very common on the Earth and on Mars as well. Mars is predominantly a basaltic planet, but it's how these rocks, these basalts, have been altered by water that ultimately has chosen, you know, Gale as the landing site.
Well, let's talk about driving for a second. Chris, when we say driving the rover, I mean, it's tempting to think of somebody with a joystick, but of course it's not that.
Well, the rover drives based on a series of commands that are sent up to it the day before. So every day, the rover operations team will send a bunch of commands and tell it what to do for the next day. They will tell it, drive 30 metres in that direction, and it will just go in that direction. It has hazard avoidance cameras that will warn if there's something in the way. So if it finds a particularly big rock, or if it discovers that one of its wheels might be slipping in soft sand and therefore risk getting stuck and so on, it will stop and say, well, tell me what to do.
How fast can Curiosity go?
It's not very quick when it's actually driving. It's only about 30 metres an hour as an average, the same as a garden snail, I think, yeah.
Okay, well, I can imagine that. It's a robot, nuclear-powered, laser-equipped snail on Mars. I can just about get my head around.
But Curiosity is designed to drive for 20 kilometres. The science targets are only 8 kilometres away, so hopefully it can drive much further than that.
So what is the first science target? Where are we going?
We're going just to the east. It's about 400 metres, a target called Glenelg. And this is interesting to the science team because it seems like there are 3 different geological rock types that we're looking at from orbit, from spacecraft images. And so they have different textures, they may have formed in a different way, they might have different chemistries when we look at them up close. And so each one of these can tell us a different part of the history of that area.
What does understanding Gale tell us about the possibility of life on Mars?
Well, understanding the geology tells us that, you know, what the environment was like when the rocks were laid down and how they've changed. Now, it's the environment of Mars that, you know, tells us how habitable areas like Gale Crater actually were in the past. And so we understand whether life as we know it, if it had the conditions necessary, so if it had liquid water or the energy or the right elements present to actually survive on Mars early in its history.
But Curiosity's not actually going to ask, was there life there? It's just going to ask, was it habitable? Could there have been life there?
I've seen a few people talking about fossils. Is there any hope at all? Or you're talking about sedimentary rocks after all, which is where you find fossils on Earth.
It is. I mean, the cameras will be capable of seeing anything like that, but we don't expect to see anything as big as fossilized, on Mars. Instead, when we're talking about life, the possibility of life on Mars, we're talking about microbial stuff, very early in its history and very, very small. And so the instruments on Curiosity are designed to analyze the organics, the rocks, the minerals and things, but probably isn't capable of actually finding those microbial stuff.
All I will say is that I expect the unexpected. Well, thank you, Peter, and both Chris's.
Hi, I'm Jessica Samuels, member of the Engineering Operations Team, and this is your Curiosity Rover Report. Last week, we completed our second round of vehicle health checkouts. This was primarily targeted on the robotic arm and the hardware at the end of the robotic arm called the turret. This included the different instruments and the sample processing hardware and sample acquisitioning hardware. Our arm checkout activity was in preparation for our first contact science. This is an exciting time for the robotic arm team and the mission as a whole, as we will be doing our first placement of an instrument on a target called Jake Matijevich. Our target was named specifically for our Surface Operations Team Chief Engineer, who unfortunately passed shortly after landing. The target Matijevich has been selected to cross-calibrate two of our instruments on the rover, the Alpha Particle X-ray Spectrometer, which resides on the end of the robotic arm, and the ChemCam instrument, which resides on the top of the remote sensing mast. Recently, we completed a mass-cam panorama of a ridge, which will give us a great vantage point of the Glenelg target area. A few sols ago, we completed an interesting campaign where we actually acquired images of the Martian moons Phobos and Deimos transiting across the sun. So that was your Curiosity rover update. Check in for future reports.
Welcome to NASA's Jet Propulsion Laboratory in Pasadena, California. I'm Veronica McGregor. We're here to give you another update on the Curiosity rover mission on Mars. Today is Sol number 51. That marks 51 days, more or less, that the rover has been exploring the red planet. If you were there right now where the rover is, it's about 6 o'clock in the evening local time, and it's late winter, just a couple of days away from the start of spring. Let me introduce the science panel that is going to bring you up to date on some of the recent exciting discoveries on Mars. We'll begin with Dr. John Grotzinger. He's the project scientist for the mission. He's with the California Institute of Technology. Dr. Mike Malin with the Malin Space Science Systems in San Diego. Rebecca Williams, she's with the Planetary Science Institute in Tucson, Arizona. And Bill Dietrich with the University of California at Berkeley. And we're going to begin with John Grotzinger.
Thanks, Veronica. So I'll just bring you up to date a little bit on where the rover is. As Veronica said, it's the evening of Sol 51, and the science team is now planning Sol 52's activities. It's been about 3 sols since we left the rock that we called Jake Matijevich, and that rock is the first place where we actually put out the arm and took images with the MOLLE camera and also the APXS instrument, which gives us chemical composition. And now we've driven quite a long way. Yesterday we had our longest drive of quite a bit over 50 meters, maybe 53, 54 meters. And we are most of the way now to Glenelg. And what will happen now is that the science team is busy trying to choose a target to collect material, probably sand, probably windblown sand, that we will put into the chemical laboratories for the first time on this mission, into the SAM and the ChemMin instruments. And that's an activity that will take on the order of 2 to 3 weeks. So we're choosing this target carefully so that we can do as much science as possible there. Okay, so as we were driving along on the way to Glenelg, we encountered some really interesting outcrops that were surprising to the team. And in the first graphic, what you'll be able to see are these outcrops. And this is one of them. It's named Hada. And to us, it just looked like somebody came along the surface of Mars with a jackhammer and lifted up a sidewalk that you might see in downtown LA in sort of a construction site. So you can see this rock unit, and it's about 10 to 15 centimeters thick. So it's sort of on that scale, and it's tilted in the perspective you're looking at. It's tilted off to the right. And what it does is it exposes the materials that make up this slab of rock. And there's a couple of these, and what we're going to be presenting today, my colleagues here will show you what represents the consensus opinion of the science team that this is a rock that was formed in the presence of water. And we can characterize that water as being a vigorous flow on the surface of Mars. And we were really excited about this because this is one of the reasons that we were interested in coming to this landing site, was because it presented from orbit quite a strong case that we would find evidence for water on the ground. Turns out that, in fact, we landed on this unit, and this makes a great starting point for us to do more sophisticated studies using the rover payload. So what I'll do now is turn it over to Mike.
Thank you, John. I'm here sort of as the ghost of briefings past. I'm going to show you how we had anticipated with the design of the cameras this type of outcrop, and how when I briefed the media at the launch briefing for science on the 23rd of November, I actually used as an example, this would be the type of rock the cameras would excel on. To remind you, the MASS cameras, there are two of them. One is a 34 millimeter focal length, which is sort of a moderate wide angle, and then a 100 millimeter, which is a telephoto lens, gets about 3 times higher resolution. If I can have my first graphic, you'll see this is a slide from the November 23rd presentation, which is a conglomerate bedrock outcrop in central Utah. It's about 100 million years old, and it's really a rock made out of a bunch of pieces of gravel. It's a rock made out of rock. And the squares, the white squares, are enlarged at the bottom of this graphic. If you look at the one on the right, you can see there are a few bands of light tone intermixed with sort of a speckly texture. The speckly texture is the conglomerate, has lots of little pebbles in it. The lighter tone things are sandstone. So there was sand moving down a stream along with cobbles, and you'll see a little pebbles. You'll see that a little bit later in this presentation by Bill Dietrich. But this is the view that we get with the MASS cam from 100 meters, from a 50-meter distance. And the next slide shows if you got to 10 meters distance, what you see in either the 34 millimeter camera at the top or the 100 millimeter camera at the bottom. You can see that the particles, the pebbles, are about 1 centimeter or 2 centimeters across, and the bed of sand you can see is roughly the same. There are layers in the bed of sand that are roughly the same thickness. These are water-lane sediments that were then turned into a rock, and then that rock has been eroded away, showing us this large outcrop. The next slide shows a feature on Mars. Our first view of this similar type of rock came where the landing engines blew away the dirt and unveiled this layer beneath the surface debris. And you can see in the upper left corner an enlargement of the white box that shows that there is a layer there that seems to have rocks embedded in it. We have a higher resolution view of that in the next slide, which was taken with the Mastcam 100. And you can see in the lower left now that the gravelly surface and the gravel at the edge of this layer, this is a relatively thin outcrop of the materials you're going to see in a few minutes. But basically, we had anticipated and discussed both before the launch and right after landing that where we were going should have these water-lane sediments that have been turned into rock. And Becky is going to talk a little bit more about the rocks themselves.
So from the Bradbury landing site, we knew we were seeing a different type of material, one we really haven't seen on Mars before. And we were hoping that as we proceeded to Glen Elg, we would see additional exposures of this type of material that we could investigate further, specifically with the Mastcam 100. If I could have my first graphic, please. So this is the HADA exposure that John introduced you to a few moments ago, and we were just really extremely fortunate to have such an ideal viewing geometry of this material. This is a fractured rock outcrop that has been naturally tilted, and it's just an ideal viewing geometry for the Mastcam 100 to look at the fine-scale textural properties of the rock. When a geologist goes into the field, what they want to do is see a fresh exposure of rock to look at things like the grain size, the shape, the color, and the arrangement of those grains, and that tells you a lot about the formation history of that rock. So with the Mastcam 100, we acquired these images on Sol 39, and I'm going to zoom in on the lower left-hand portion of the screen. What you see is this rock is made up of rounded gravels. There's one circled for you at upper right, and a matrix that's very sand-rich. And these attributes are consistent with a common sedimentary rock type called a conglomerate. Now the class that is circled is about 3 centimeters across. It's roughly the size of the gravel that I'm holding in my hand. And you'll see that the perimeter has a very rounded shape. It's been worn by abrasion in a sediment transport process. You'll also notice the gravel is sticking out from the rock. And over time, erosion is working on that rock face and liberating some of the gravels, and they're falling down and accumulating on a pile at the base of the outcrop. In the next slide, a second exposure of this very same material we saw on Sol 26 and imaged it with the Mastcam 100, the narrow angle, on Sol 27. And this outcrop's name is Link. You see very similar textural properties that we saw at Hada. Again, very rounded gravels in a light toned sandy matrix. And again, we have that gravel pile that's adjacent to the rock outcrop. So by looking at the size and shape distribution of the gravels that are not only in the rock outcrop, but those that we infer were liberated from the rock outcrop there on the surface, we can get a good idea of the range of gravel size and shape properties that you see there. In the next slide, we'll zoom in, and there's another one of these rounded gravels that's about 1 centimeter across, so it's roughly the size of a plain M&M. And geologists are interested in rounded gravels because they tell you that those particles have been subjected to a sediment transport process, either by water or wind. And so typically you start off with a very angular rock fragment, and as it's transported, it's bouncing along, interacting with other grains and the surface, and that wears away the edges until you have a very smooth surface, such as you see here in this pebble. And the key components of these gravels that we're seeing here are, one, the rounded shape, but also the size. These are too large to be transported by wind. The consensus of the science team is that these are water-transported gravels in a vigorous stream. On the right of the graphic, you can see a typical stream bed deposit. It's a gravel conglomerate that has gravels of the same size and roughly the same roundness as we see on Mars. And so this is just wonderful ground truth confirmation of this water-transported material that was predicted based on analysis of orbital images. And now Bill will talk about the potential source of these gravels and also further details of the water transport process.
Thanks, Becky. So I'm going to ask the question, where did these gravels come from? And what was the environment like at the time of deposition of the deposits we now see at the rover site? And to do that, I'm going to use a term called fan, and specifically alluvial fan. And to explain that, I'm going to take you on an aerial tour, first through Death Valley and then back to Gale, and connect the dots between the fan and the deposits we see. So if I could have the first video, I introduce you to an area you're familiar with. There's Los Angeles and there's Las Vegas, I-15 between. And we're going to take a flight just to the right of Zizix, and where there are 6 fans outlined in white that illustrate the form and process that I want to talk about. So we'll zoom in, and you'll see the 4 that are facing us, the white lines delineating the lateral boundaries of sediment deposition that has occurred as a consequence of sediment and water rushing out of the canyons that are on the hills there. And we'll now go up to the headwaters, and we see the stream confined a canyon. And then it reaches the front of the mountain, and as water and sediment rushes out, it spills. And as it spills, it forms a sheet of water, or it runs out as discrete channels, and you can see them there, shifting right, shifting left, As it deposits, it elevates and shifts right, left, back and forth, building the fan structure that's so characteristic and so identifiable. We've rotated it across this white tone fan, and now we're settling down and looking back. So now you see the fan shape, just like a fan you'd use to cool yourself on a hot day. You see the white outlines of the structure, and you see how it's a result of water and sediment pouring out of a canyon. So if I could now go to the next video, we're going to go to Gale Crater. And we're flying from north to south, and you see in red lines the lateral boundaries of a fan, just like what we saw in Death Valley. And we're looking down at a canyon that is about 11 miles long, 2,000 feet wide, and about 100 feet deep. And that canyon was cut by stream flows, and that stream and sediment then entered the crater rim wall and spilled out left and right, and the blue lines delineate distinct channels that we can recognize, fossil beds if you like. We look at these channels and we see that they cut across the fan system, and to us they suggest that this fan did not form in a single instance, but this records some duration of a process. Now we settle down, and there's Curiosity. It's about a 2 to 4 mile hike from the nearest channel to Curiosity, all downhill. So we think it's reasonable to suggest that the water and sediment came down that fan that we see now, the sediment at Curiosity. And looking back, you see a watershed. You see a canyon, you saw a fan, you see channels. Now, what was it like then if you were standing at exactly Curiosity site at the time of the sediment deposition? And the next video will show that. So here is water moving sand and gravel. It's a vigorous sediment transport process, bursts and sweeps of turbulence, mobilizing together sand and gravel. And of course, the consequence of that motion is collision, breakage, and rounding of particles. And in a flow that we can estimate for the rover site that might have been from ankle to hip deep and maybe moving a few feet a second. And we arrive now at what the bed of the rover site might have looked like after the last flow, of course visited by a few earthlings. That was the Atacama Desert. And you see the heterogeneous bed, you see the patches of sediment, and what we can think about then is that we were in a watershed. We saw going from an uplands to a lowlands, and we would start with a rock that would be big and broken like this. And it would travel something like 20 to 25 miles and end up something small and rounded like this. This, going from this to this, is direct visual evidence of the wear by what we call bedload transport, of the wear particle collision and the transport by water to the site of interest. So we can see from these stones, as Becky has described, are very revealing to us about the process and even the potential of connecting Curiosity to the fan system we observed at the site.
Okay, so thanks, Bill. I'll just wrap up here and summarize some of the key observations that allow us to tell you about this story about water flowing on Mars. So first of all, this represents a great collaboration between the Curiosity rover and the orbiters that are routinely mapping Mars. Now, in the case of looking at the alluvial fan, we see that that's provided by both the HiRISE imager, the CTX imager, previous generations of imagers look at these features that geologists have long thought of as alluvial fans. But now that we're down on the ground with Curiosity, we can see the textural evidence that Becky and Mike talked about, where you see the individual pebbles, the rounding, the geometric relationship that they have to each other that gives us a sense for that. So if we just go back one, please. We should be able to see where these different features occur on our route to Glen Elg. And so Goulburn was the outcrop that Mike talked about, the one that we got for free way back when the thrusters blew the soil away. And at that time, the team came up with a number of hypotheses to potentially account for this. And then we had a lot of discussion about it. And then we worked our way to Link, where we were able to see the first of the outcrops that Becky talked about. And we began to wonder about the stream flow option as being the most likely candidate. And it was really when we got to Hatta where we saw this again most clearly that it was very easy to reach team consensus to come with you to come to you and present this story about where we are. Now the rover is currently about 3/4 of the way between Hatta and Glenelg, and we're working our way down into that key area where these three terrain types come together. So if we can go to the next one, again, just to remind you something that we showed you before we landed in the press conference before then, we see the alluvial fan in Peace Vallis, which is now an official name that the IAU has approved as the entry point for water into this feature. What we were uncertain of at the time of landing was whether or not this alluvial fan extended all the way down into the landing ellipse. And you see where we landed is quite a bit away from where you would identify, as Bill said, it'd be a few miles hike to get to the base of the alluvial fan. So it looks like, at least intermittently, that fan extended down to where the rover was. That's our most popular hypothesis right now for the team. The other part of the story that we talked about is in the last slide, where you now see the map of this feature called thermal inertia. So we're beginning to get a sense of what that might mean now, because you see the X where Curiosity landed, and you see high values of thermal inertia, but not the highest values. So we wonder what might cause this greater retention of heat, and it could be because you're dealing with materials that are consolidated. And what we haven't told you today is anything about the rest of the payload, what we might measure in terms of the chemistry, what we might measure in terms of the mineralogy. What we do know is we go down towards Glenelg, we're going to go towards that red patch, which is where the thermal inertia becomes the highest. And so our plan as we go forward now is to study the chemical and mineralogical attributes of these rocks and see how water may relate to the cementation of these gravels to form a rock. And that's really where it brings us, is to really the beginning of the science mission, where we have now discovered evidence for water, and what we'd like to do is to begin to characterize habitable environments. And that requires using all of our payload, including the instruments that measure the chemistry and the mineralogy. So we'll keep you updated as we go along with those measurements as well.
Okay, we're going to open it up to questions. I'll start by asking if there's any here at JPL, and then we'll go to some of the folks on the phone line. So we'll begin right here, and just wait for a microphone to come to you and give us your name and affiliation. Thanks.
Hi, Mark Kaufman with the Washington Post and National Geographic. I wonder if you have any estimate for the length of time that the water might have been running, or any estimate of when it might have been running. I have a follow-up question as well.
Yeah. Okay. We at this point, you chose your words well. Estimate. We see clear evidence of multiple channels across the fan, and we actually see quite a difference between what is the western portion of the fan and the eastern portion of the fan, and we interpret that as a period of time of significance to build progressively the fan. So we can step away from the idea that it was a single burst of water that ran down the canyon and built it all in a day. There's too many things that point away from that. We would anticipate that it could be easily thousands to millions of years, but this is what the importance of finding these grain sizes, because we can start to calculate the water transport needed to move the gravel. That then constrains the discharge of water. We can put the water in the channels. We can begin to calculate how long that would take. So this is opening the door to answer your question quantitatively. I'm comfortable to argue that it's certainly beyond the 1,000-year time scale, but we're still gathering data to go further with that. I think we can now go further because of what we're seeing.
Okay, do we have a question here in the front? And then we'll go to a phone line right after you.
Claudine Muller, Le Monde. You've partially answered, but still I would like you, either of you, to answer the controversy on the choice of the site. Some research that was recently revealed saying that the clays on Mars could not be due to water, but to magmatic precipitation. I'm sure you're aware of that research.
Yeah, I think, the thing about Curiosity is that we have the ability to detect clays if we encounter them. And then what we're going to do is we'll study the context in which those clays occur and pick amongst the various options that are on the table. So right now, we have no opinion. We haven't found any clays yet, but when we do, we're going to fit them within this context that you're hearing about today.
Okay, we're going to go to the phone line and take Irene Klotz from Reuters.
Hi, thanks very much. I have a couple of questions. First, I just wanted to clarify that this very interesting research you're reporting today, this was all based on imagery. There was no mineralogical or chemical analysis. Is that right?
Yeah, that's right, Irene. The thing about it, in some cases, when you do geology, a picture's worth 1,000 words. And in this case, the team felt in discussing, really, this is just one of these cases where it's kind of all about the images that brings you to this point. But the images only get you so far. You look at the rock that's still up on the screen there, and you wonder, why is it as hard as it is? For that, we really have to get into the chemistry and mineralogy, and that's the next step for us.
Thanks. And just to let you know, John, I was listening to you in Death Valley. I understand that on Earth, the tilting would come from plate tectonics, but what would account for that break and the tilt on Mars?
Yeah, so there's a couple of options. That's a good question, and the science team is actively discussing and debating what the options are. I think the simplest scenario is that somewhere near this outcrop, a small impact occurred and just simply lifted the beds up and rotated them. But there are other options as well.
Okay, we'll go next to NPR, Joe Palca. Go ahead.
Hello?
Go ahead.
Well, if you called on me, I can't hear myself or you, I'm afraid.
Can you hear me now, Joe?
Yeah.
Okay, go ahead.
I think I can. You can hear me, I take it.
Yes.
Two questions then. One is, do you have any idea how long ago this event took place? And the second is, can you say anything about how the rock became embedded with water? How the rock, you said that there were pieces of rock embedded in rock, and I wondered how that process happens.
Mike, why don't you take that?
Okay, let's see, what was the first part of it?
How old is the rock?
We have no real way of estimating ages on Mars quantitatively. This is these are old rocks. It is possible they were actually buried under the materials that the mound is now made out of, that the mound that we see now, the mound has retreated to uncover these features. That's a possibility, which would make them extremely ancient, or they may be somewhat younger, but probably several billion years would be the canonical estimate by most scientists about how old things are in this region of Mars. How we got the rock, basically what's happened, as Bill described, you had water transporting these gravels down to the downslope to the bottom of the fan. At that point, they just stayed there. Other materials were deposited on top of them, and eventually they were cemented together by salts or by carbonates or some other material to act as a means of holding the rock together. And then since then, they've been uncovered again, and that uncovering has revealed this resistant rock unit. But basically, it was gravel that was transported by water, sat on the surface for a while, was then buried and became lithified, turned into a rock thereafter. So it's a rock made out of other pieces of rock, and that's what we see at the surface today.
Okay, thanks very much.
Okay, next we're going to Craig Kovalt on the line. Go ahead, Craig. Craig Kovalt?
Hi, this is Craig Kovalt with Space Ref and Aerospace America. Can you hear me okay?
Yes, we can hear you. Go ahead.
A couple questions relative to the alluvial fan down in the bottom of the crater there. What does it speak to relative to what was going on above the crater rim relative to water and the nature of water? of course, via the imagery from MRO and the previous orbiters. And then I have a second follow-up.
Okay, so the area that drains the head of that canyon is about 200 square miles or 500 square kilometers. We see traces of smaller tributary gullies in that area. So it suggests that there were concentrations of water that entered then the larger canyon that then did the cutting. Where the water come from and the mechanism of delivery is something we're exploring currently. That water then ran down the canyon, though, and transported sediment across a slope of just about 1%. It's a very gentle gradient fan, and apparently continued down to where our landing site is.
Okay, my second question is, pardon the pun, but given the Mars exploration since Mariner 9 and these alluvial sands, really, is this really a watershed moment for the for the Mars exploration program, given the history going back to Mariner 9 and all the orbiters since?
I think, Craig, it sounds like you're scuba diving right now. I'm not sure we got all that, but if you're asking, what is the profound significance of this discovery, I think the reason that we're coming out with this as early as we are is because I would guess at this point in the history of exploration in the Mars program, we're getting better at being able to integrate the orbiter data with predictions about what things define on the surface. And so I think for a geologist to look from orbit and see an alluvial fan and then see a conglomerate rock that looks like it was transported in an alluvial fan is not rocket science. But it is exactly the reason that we chose this landing site, is because from orbit there are some signals that are very clear, and you build your course of exploration built on those foundations that you think you're most likely to be able to establish. And I believe that's what we've done now. And so as we go forward now, we bring the rest of the payload in. We look at more rocks. We get more context. And the question about habitability goes just beyond the simple observation of water on Mars to recreating the environments in greater detail with an understanding of the chemistry that was going on at that time, to ask if this is the kind of place that microorganisms could have lived. So certainly flowing water is a place where that could happen, and this particular kind of rock may or may not be a good place for us to preserve those components that we associate with a habitable environment. So that's still to be determined, and that's the research the team is working on.
Thank you.
Okay, the next caller is Randy Shostak with EOS Magazine. Go ahead. Randy Shostak with EOS Magazine. Okay, we're going to go to the next caller, and that would be Leo Enright with Irish Television. Go ahead, Leo.
Thanks very much. A couple of questions, if I may. My first question, this is obviously a stunning announcement, and I mean, quite an extraordinary result at an early stage. And I'm not a geologist, I'm a journalist, so I'm asking you, why did it take you so long to make this announcement? I mean, it seems that any first-year geology student would have looked at that exposure and said immediately, that's water transport, high speed, all of that. Was there somebody saying, hang on a minute, this could be something else? And if they were, what was that?
Yeah, well, so Leo, thanks for that. I actually, it turns out that really there's some details here that matter that may or may not be worth getting into. But, there are options. And so, the sort of the putting this in the context of a jackhammered urban sidewalk, actually, if you take concrete as a substance, it is not something that remains liquid because water is flowing freely across the surface and being vigorous. It's really, in a geological context, something called a debris flow. And I would say, then you've got a more viscous material. And we are interested in the details of how the water expressed itself on the surface. And so we do keep in mind these alternative hypotheses as we look at this. And I think you have to look at this rock in a lot of detail and see it in a couple of places before you feel confident as a science team moving forward with a majority opinion that really this is more likely the result of water flowing vigorously across the surface rather than just sort of sluggishly pushing along in a pile of watery debris. So to the extent that that makes a difference to you, that's a nuance that we were interested to pursue.
And my other question, my other question related to really the process of humans versus robots. Tomorrow is Researchers' Night throughout Europe, and in Ireland, as it happens, in Galway, they'll be discussing the benefits, the possible benefits of astronauts versus robots in planetary exploration. So I wondered, did you have any thoughts for that audience as to, having made this extraordinary early discovery, does this tell you something about the relative merits of humans versus robots?
Well, again, thank you for the heads up on that question by email. It allowed me to think it through a little bit. I think this is the kind of problem where this kind of rock, given the evidence we have from orbit, which is analyzed by humans in advance of landing there, when we arrive at something like this, with a robot, we can actually test the hypotheses, including the alternatives, pretty quickly and efficiently and arrive at a consensus opinion. A lot of people have asked, what about this gigantic team and how does it come together? And I would say it's just simply an issue of signal to noise. If the geological signal of the process is large enough, it's very easy to build consensus, and that's what happened to our team. So for a robot, it's easy to achieve the data that you want to get. But let's say that this was a rock that we didn't expect at all, something that provided no earthly analogs, something that wasn't easily to analyze. I think then if you're working with a robot and a very large team, it becomes very difficult to reach consensus. And therefore, there's no substitute really for a human when it comes to exploring really complex situations, because the triage that you can do mentally as you pass your judgment over the options and command yourself to walk to different places and make different measurements is really the compelling reason to want to do human exploration, because it's just so much more efficient, and you probably will arrive at conclusions that are more likely to be correct than if you had just a robot along. But we don't consider this to be a particularly complex scenario that we're looking at right now.
Okay, we're going to the next reporter on the phone, and that would be Eric Hand from Nature. Go ahead. Okay, we're going to go then to the next person, and that would be Emily Lakdawala from the Planetary Society. That was probably Eric. Oh, nope, that was Emily. Okay, we're going to keep going down. We have a lot. Todd Halverson, Florida Today. Are you on the line?
Sounds like the phone system went off.
It does.
All right, let me see if there's any questions here while we go try to find any callers. And I don't know if there's some folks over. Okay.
I wanted to go back to that question of habitats and habitability. What do you think this, the finding that you have right now tells us about this site and perhaps the, implications for the larger site around that where you're going to be heading in terms of Glen Elg? You said, I believe, that this is a potentially habitable place. How significant is that in terms of the overall mission of Curiosity, which is to find habitable places?
So that's a very important aspect of the mission. It's maybe the core of the mission is to explore for habitable environments. So again, just to remind you what a habitable environment is, it's one that has water, sources of energy for the microorganisms to utilize for their metabolism, and then a source of carbon to build structures. So in that in that sort of flow. That's what we're doing here. And now we've got a hall pass for the water observation. And now we're going to move on to the chemical building blocks of life and do the elemental chemistry and the mineralogy and see if everything adds up to the kind of scenario where there would be, you could reconstruct the kind of energy balances that might have occurred in this particular ancient environment. Then the last one is the most difficult of all, I believe, and something we've said clearly all along. You know, finding evidence for preserved organic carbon is not easy on Earth, on a planet that teems with life and has lots of water. You go back to rocks that are billions of years old, and what you discover is that the very process that enables life to be present, water, if you have too much of a good thing, it's a mild oxidant, and it actually results in redistribution of those large organic molecules into things like carbon dioxide that just drift away. So there's a part of this game that we refer to as preservation, and we look at a rock like this and wonder, okay, well, it might have been a habitable environment, but part of that is it the kind of thing that might preserve organic carbon? And if you have your choice between one kind of rock and another kind of rock, you know, we would look at this, and this would be something that I think we would probably want to drill at some point and use the SAM instrument to inspect. But there might be other things that have a higher potential to have preserved organic carbon than this. So the point of the mapping that we're going to be doing as we go around is to look at these different kinds of rocks and assess their potential for preservation, and then try to rank those in terms of our priority. But this is just our first. So it would be a prospect, but maybe not at the top of our list.
Okay, we're going to go back to the phone lines, and Todd Halverson from Florida Today, you can go ahead.
Thanks very much. Todd Halverson of Florida Today. I guess for John, could you give us a general estimate of when you expect to get to Glen Elg at this point? And I was wondering if you could kind of give us a sort of a real general idea on the go-forward plan from South 52 and beyond.
Right, so we've got probably a couple sols ahead of us where we're looking at targets that the rover will want to scoop. Our first step in putting materials into the SAM and Chemin instruments is to acquire a loose material. We have a requirement to do that, and we have a couple of nice targets that are within somewhere between 2 and 3 and 4 sols in front of us. And then when we get to that target, we'll park for what will seem like a very long time. It's going to take on the order of at least 2 weeks, maybe 3 weeks, because there's such a complex set of processes that we have to go through using the rover that have never been done before on Mars. And obviously, because it's what we call a first-time activity, we're going to be conservative, we're going to go slowly, we're going to make sure that everything is working in the sequence that it should. And then after that, we will proceed to the final Glen Elg destination, where we'll look around and then begin to evaluate what our first candidate will be for drilling.
Okay, we're going to go now to Ken Kramer from Spaceflight Magazine. Go ahead.
It should. And then after that, we will proceed to the final Glen Elg.
Ken Kramer, you have to turn down your television. Let me ask you a question that came in from Emily Lakdawala, if I can go ahead. She said, do conglomerate rocks present particular difficulties for drilling and sampling because of their heterogeneity?
That's another good question. This particular rock that we're looking at, yes, they do. We would consider this to be a challenging rock because the particles that make it up, you see that they weather out as discrete bits of gravel, as Bill and Becky were showing. And the fact that they weather out and they retain their original shape so well suggests that it's cemented, but probably not completely cemented. And so what we would worry about by drilling this rock is that maybe it would fragment and break along the boundaries between each one of these bits of gravel, and we might not actually get much material up into the drill bit. So the project now is looking at these kinds of rocks and collecting analogs from Earth to begin doing some testing with to make sure we're ready to wrestle with something like this.
Okay, and there's one more from Emily before I go to the phone line. This is when Twitter comes in handy, when the phone doesn't work. let's see. Are you chagrined at all that you didn't stop at Hatta to investigate with Molly, or did Mastcam 100 give you all you needed?
Well, that's an easier one. In that case, we weren't really able to use the arm. We had to go through Cap 2 in order to be able to use the arm, and that was so many weeks out into the future. We made the decision to drive away. But now, having seen these similar rocks in 3 different locations, we have confidence that at some point we'll find another one that looks similar to this. And if not, then remember that the name Glenelg is a palindrome chosen by the team to represent that we're actually going to be passing by here again on the way out. So we can recover that if we need to.
Okay, we're going to go back to the phone line, and Carl Franzen from Talking Point Memo, are you on the line?
Hello, can you guys hear me all right? I can barely hear you.
Okay, yes, we can hear you. Go ahead.
Okay. Yeah, I just wanted to, following up on, thank you again for hosting this and explaining everything that you found so far. It's a really exciting announcement. Hello? Can you hear me?
Go ahead, yes.
Yeah,
You
okay.
might need to turn down your
Yeah,
TV.
so following up on an earlier question, I just wanted to ask, I mean, is there any way that we'll be able to tell either now or later on from analysis of the rock and soil samples whether or not there was anything living in this water, whether that was on the stream bed itself or flowing through the stream, and you know, or is that not even in the cards here, or is that a possibility, I guess?
It's certainly a possibility that we can try to look, and to be brief as possible, this just requires us to sample the rock, collect some portion of it, and be able to look for organic carbon, which is one of the objectives of the mission. And if we find it, that in its own right does not require that there was ever living microorganisms here. There are lots of other ways that organic carbon can be introduced to the surface of Mars by inorganic processes. And one of the great things about a river system like this is that it could potentially collect those materials from much farther away than the rover is and bring them right to us. And so, you know, this is definitely something that if we can, we would like to drill at some point and do that exploration.
But you said the carbon could be from, you know, like you said, a variety of sources. So is there any way to decisively know, based on studying it using any of the instruments, whether or not it came from a living, you know, organism?
Arguments like that are based on a preponderance of evidence, and when we take that argument to the Earth and go back to rocks that are billions of years old, we require multiple lines of evidence. And Curiosity has the ability to detect organic carbons and actually tear them apart in some detail. But it's going to have to wait to another mission to be able to definitively demonstrate that.
Okay, thank you. Helpful.
All right, we're going to take our last question from the phone line now, and that would be Ken Kramer from Spaceflight Magazine. Go ahead. Okay, no, Ken has dropped off the line. All right, we're going to wrap it up then here. Ken, just go ahead and contact us another way, and we'll get your question to the panel. And I just want to encourage everyone to continue to follow this mission. We post updates daily, and we have plenty of videos that go along with the mission each week, posted on Thursdays. You can find everything at nasa.gov/MSL. So just continue to follow us and join us with the journey of curiosity. Thank you so much.
Hello, my name is Sanjeev Gupta and I'm a long-term planner for the Mars Curiosity rover. This is your Curiosity rover update. We've now been on Mars for almost 2 months and we've been witnessing the amazing new vistas of the never-before-seen Gale landscape taken with our wonderful cameras. However, much of the science team have had their eyes and the rover's eyes firmly focused on the ground. On the drive from the Bradbury landing site to our current location, we have been analysing 3 really interesting outcrops that we have called Goulburn, Link and Hotter. If we look at the Hotter outcrop, we can see a distinct layer that has been tilted and eroded, and this allows us to look at the cross-section through the layer. When we looked at the layer with our high-resolution Mastcam camera, we found that it was comprised of sand grains and small pebbles that had become cemented to form a hard layer. Here, you can see a pebble that is 3 centimeters in diameter, so smaller than a ping-pong ball. This suggests that this layer is an ancient gravel deposit. The surprising thing is that when we looked at the pebbles closely, we discovered that many of them were quite well rounded. This is very different to the many angular clasts that usually litter the Martian surface. Here, you can see a rounded pebble from a riverbed on Earth. On Earth, rounded pebbles are a common telltale sign of rocks that have been transported by water, for example in a river or stream. As water flows over a riverbed, if the flow strength is great enough, the pebbles are lifted up into the flow or rolled along the riverbed and they become pounded and battered against each other, and this causes them to become rounded through time. So what we think we might be seeing here on Mars is an ancient riverbed with the pebble beds representing old stream deposits. The size of the pebbles tells us that these rocks could not have been transported by the wind, so it seems clear they must have been transported by water. So how did this pebble deposit get to be here? If we look more broadly in Gale Crater, we can see that there is a prominent feature that geologists call an alluvial fan. Alluvial fans are cone-shaped deposits of gravel and sand that accumulate where streams exit mountains. In Gale Crater, there is a 10-kilometer long fan formed at the mouth of a 30-meter deep canyon that is derived from the crater rim. On the fan itself, we can see evidence for multiple channels suggesting that the stream bed direction changed through time. When we look at the location of the Curiosity landing site with respect to the alluvial fan, we see that the rover landed downstream of the fan. The rounded pebbles likely represent long-distance transport down the alluvial fan. So this is really exciting news for the science team because it's the first time we are seeing gravel transported by water on the surface of Mars. This has been another exhilarating week for Curiosity on Mars and for the science team here in Pasadena. This has been your Curiosity rover report. Check back for more updates.
Hi, my name is Daniel Illuminati. I'm the Surface Sampling and Science Phase Lead, and this is your Mars Curiosity rover update. Curiosity is still heading to Glenelg. We've just stopped at the Bathurst Rock Formation to check it out with the robotic arm-mounted instruments, a hand lens imager and a spectrometer. Got some great science data there for the science team. And now we're moving to a new location called Rock Nest. And we've come to Rock Nest because it has nice wind-blown sand drifts. At the Rock Nest location, we really are entering a new phase in Mars exploration with Curiosity. We're starting the surface sampling part of the mission. The reason this is a 1-ton rover with a 200-pound robotic arm is because we have these tools to acquire bits of Mars, either with a scoop or with a drill, process those samples for our very sensitive analytical lab instruments. So our scoop, this is not a giant backhoe on Mars. We basically have more like an oversized tablespoon attached to the end of the arm, and we grab on the order of 20 grams of material, and we position the arm over the soil target, and then we just actuate the scoop, do a little bit of vibration to kind of level out the sample, and then raise the arm up, close the scoop, and carry on with our sampling activity. Over the next 2 to 3 weeks, we'll be doing these scooping and sample analysis activities. And then from there, we expect to spend a few more weeks driving over to the Glenelg area proper, doing scratch and sift science along the way with the robotic arm. And once we get to Glenelg, we'll look forward to some exciting first-time drilling activities. This has been your Mars Curiosity rover update. Check back for more reports.
Hi, I'm Noah Warner, Tactical Uplink Lead for the Mars Science Laboratory mission, and this is your Curiosity rover update. Curiosity is currently at the Rock Nest location inside Gale Crater. When we first arrived at Rock Nest, we performed a wheel scuff maneuver. This is our rover's version of kicking up the dirt with your hiking boot to determine if the Rock Nest area was indeed a good first scoop target. The first scoop was successfully performed on Sol 61, and the entire team was excited to see the Mastcam images showing the scoop full of dirt, as well as the video of the vibration activities performed with the turret-mounted tools. This vibration allows the team to level out and remove any excess sample before closing the scoop, and it also provides some insight into the makeup of the soil. Any large particles would tend to float up to the top as the entire sample is vibrated, much the same way you would shake out the marshmallows in your box of Lucky Charms. Looking carefully at images, the team noticed a bright object lying on the ground just in front of the rover. We typically call something like this FOD, foreign object debris. The ChemCam remote micro imager captured a high-resolution image of the object showing that it is most likely a benign piece of plastic or shrink tube left over from a terminated wire. This could have possibly come from the rover or from the descent stage separation event during landing. Curiosity processed the scoop sample through Chimera, our labyrinth of passageways at the end of the arm that we use to sieve and portion the soil sample. We did some internal sandblasting by vibrating the sample at different orientations of the turret in order to remove any internal contamination. The team dropped the first scoop off to the left side of the rover, and in upcoming sols we will make our first attempt to drop off sample to the observation tray and the Chemin instrument. We plan to be at Rock Nest for the coming week to complete our scoop activities, and then we'll get back on the road to Glen Elg, where we'll be looking for our first rock to drill. That's your Curiosity rover report. Check back soon for more updates.
Hello, my name is Bettina Pavri, Payload Downlink Coordinator, and this is your Curiosity rover update. Curiosity continues scooping at Rock Nest this week. The Mastcam and Navcam instruments provided images and video used to assess the success of the scooping and sample processing activities. These images also provided confirmation that the sampling system was successfully cleaned after the process was completed. Also this week, a soil sample was dropped off to the rover's observation tray for assessment by the science team. This sample was determined to be suitable for drop-off to the Chemin instrument. The Chemin instrument uses X-rays in order to image the sample and determine what minerals make it up. This helps geologists understand how the rock formed and how it's related to other rocks we've studied so far on Mars. Scientists identified numerous bright grains in the soil because of the small piece of plastic from the landing event that had been found earlier in the week. The team proceeded cautiously, dumping the second scoop collected and imaging the bright grains. These bright grains were later determined to be components of the Martian soil, and therefore the sample was deemed to be suitable for delivery to the Chemin instrument for analysis. The science team requested Mastcam and Navcam mosaics of the outcrops in the direction of Glen Elg to plan Curiosity's journey to this next science destination. This has been your Curiosity rover update. Please check back for future reports.
Hi, I'm Nina Lanza. I'm a postdoc on the ChemCam instrument, and this is your Curiosity rover update. This has been a very exciting week for the Curiosity rover. It delivered its third sample to Chimera to complete its cleaning regimen, and also we've done our first Chemin analysis, and we've got a second one on the way. In its spare time, Curiosity has also been making measurements with other instruments, including the ChemCam instrument, which is what I work on. ChemCam is actually two instruments in one. It includes a camera with a telephoto lens, and it also has a laser that vaporizes a very small amount of rock so that we can tell what its chemical composition is. And as of this week, we will have done 10,000 shots with the ChemCam laser. This week, we've been analyzing rocks in an area called Rock Nest, and I'll tell you in particular about one called Zephyr. This one is interesting because it appears to be made of two different types of materials. It's got this harder, more resistant material on the top, capping it, and then beneath that it has a lighter colored, softer material that appears to erode more easily. It's actually eroded into a set of natural arches, so some of our team members have taken to calling it Stonehenge. This feature is really only an inch long. We're shooting this from about 8 feet away, making the pointing very difficult. So that's why we decided to do 9 points instead of just 2, just to make sure we would hit the material of interest. We ended up hitting both the dark and the light material, and we found that there was indeed a compositional difference. In addition to composition, we've also been able to make a three-dimensional model of the surface of this target using images from the remote microimager part of ChemCam. We've also used ChemCam to measure soils, such as cristarum. Here you can see a before image and then after image where you can see the crater made by the laser. This week, ChemCam did its very first depth profile, in which we shot the laser 600 times in a single location in order to tunnel through the surface of the rock. Now, this only tunnels about 1 millimeter in depth, but it can help us understand how the composition of the sample changes from the surface to the interior. Coming up, we'll be able to use this information that we've learned from ChemCam in order to decide which targets we should hit next with other instruments. This has been your Curiosity Rover Report. Please check back for more updates.
Hi, I'm David Bish, co-investigator on the Chroniken instrument on the Mars Science Laboratory, and this is your Curiosity Rover Update. We've been spending time in an area called Rocknest, and this week we delivered a scoop of a dune to Curiosity. Chroniken performs what we call X-ray diffraction measurements on powdered rocks and soil samples. And X-ray diffraction is the best method for telling us what minerals are present in a rock or soil because it's sensitive to the arrangement of atoms in minerals. As the X-rays strike the soil sample, Chroniken shows us how mineral crystals distinctively interact with X-rays. And this image shows our first X-ray diffraction results. The diffraction signals appear on the detector as rings that represent the fingerprint of the individual minerals. The rings tell us not only what minerals are present in the soil, but also how abundant they are. The Chroniken data provide us with distinctive signatures of the minerals plagioclase feldspar, pyroxenes, and olivines. Peridot is a variety of olivine. Just keep in mind that the olivine in the soil sample is much smaller than these crystals. Roughly half of the soil consists of poorly crystalline material such as volcanic glass. Thus, the Martian soil appears very similar to some weathered basaltic soils that we see on Earth in places like the flanks of Mauna Kea, Hawaii. You can appreciate how revolutionary Chroniken is when you consider that instruments of this type on Earth are typically about the size of a double-wide refrigerator, and the Chroniken instrument on the Mars Science Laboratory is about the size of a shoebox. Chroniken has been modified for use on Earth in places such as Antarctica and the Arctic. It's also been applied for the detection of counterfeit pharmaceuticals around the world, and a modification of the instrument has been used in archaeological studies to help us understand the nature of the surfaces and how we might protect them. In the coming weeks and months, we're excited to measure more X-ray diffraction data on soils and rocks to tell us much more about the geology of Gale Crater. This has been your Curiosity Rover Report. Stay tuned for further updates.
I'm Pan Conrad, Deputy Principal Investigator of the SAM Instrument Suite on Mars Science Laboratory, and this is your Curiosity Rover Update. While our robotic explorer has been busy characterizing the surface of Mars, the SAM team has also been busy, but we've been looking at something invisible, the Martian atmosphere. SAM, or Sample Analysis at Mars, is not one instrument, but three, all of which are designed to work together to chemically characterize Mars. SAM measures chemical elements and molecules, and we do this by looking at gases. We can bake solid samples until they give up their volatile components or their gases, or we can directly inhale the Martian atmosphere through our inlet ports. The tunable laser spectrometer has a special role for SAM in that it can very sensitively detect the organic molecule methane, which has been observed from the Earth telescopically and also by the Mars Express orbiter at very, very low limits in the Martian atmosphere. We're trying to discover whether or not we can see this molecule from the Martian surface and if it has any variation from season to season. So we've already begun prospecting for methane, and to date we don't have a definitive detection. We'll continue looking during the course of the mission. In the coming months, wherever Curiosity goes, SAM will continue to sniff the Martian atmosphere, periodically looking for changes on a seasonal, maybe even diurnal basis. And that will tell us something about the dynamics of the exchange between the surface and the atmosphere. This has been your Curiosity Rover Update. Check back for more.
76 years ago, a group of Caltech students and experimenters huddled behind sandbags in nearby Arroyo Seco Canyon in the Los Angeles basin as a rudimentary rocket engine burned for about 3 seconds. With that modest beginning, the Jet Propulsion Laboratory was born. Today, JPL is sending spacecraft across the solar system and pushing the boundaries of science. To mark the anniversary, JPL hosted a day-long celebration that included special presentations and documentary screenings, live music, and the obligatory birthday party offerings of ice cream and cake.
Hi, I'm Ashwin Vasavada. I'm the Deputy Project Scientist for the Curiosity rover, and this is your Curiosity rover update. A lot of what this mission is about is figuring out the possibility that ancient Mars was a habitable environment. But we're also studying the present environment. Two instruments that help with that are the RAD instrument and the REMS instrument. The RAD instrument is a radiation assessment detector. It measures the high energy radiation coming in from the cosmic rays and the sun. That radiation is changed as it goes through Mars' atmosphere to where we detect it on the surface. These measurements are helping to understand what the environment's like on the surface so that future astronauts will know how they can protect themselves from this harmful radiation. Another instrument that Curiosity has that measures the modern environment is called the Rover Environmental Monitoring Station. It's basically our weather station. We measure a lot of things, including pressure and humidity, temperature, and wind. It's been seeing little dips in pressure around noon that seem like the signature of dust devils. Only thing is, our pictures haven't turned up any dust devils. Spirit and Opportunity saw lots of dust devils moving across the horizon. Our best guess at what's going on is that Curiosity is seeing dust devils go right over it. So what we think is happening is the same sorts of vortices driven by convection are occurring on Mars at Curiosity's site, but just not picking up dust. Another thing that REMS has been measuring is winds. Turns out we're in a pretty interesting place inside of Gale Crater. We're right at the base of a 5-kilometer high mountain to the south of us, and then there's a pretty tall crater rim to the north of us. And we're sitting kind of in a flat depression between the two. The winds blow up and down the mountain as the temperature changes during the day, and up and down the crater slopes, and then along the depression where we're at. So right now we're trying to figure out from the REMS data exactly which parts of that wind field we're measuring. With Thanksgiving coming up, we've been preparing a few days worth of commands to send up to the rover to keep it busy while people here take some much needed time off. The rover will be acquiring a big panorama of our surroundings while we're away. I'm Ashwin Vasavada, and this has been your Curiosity rover update.
NASA's Mars Curiosity rover has completed its first same-day touch-and-go inspection using the Alpha Particle X-ray spectrometer on its arm to touch a rock named Rocknest 3 and collect data about the chemical elements in that rock. The rover then stowed its arm and drove 83 feet eastward toward a target called Point Lake, a spot from which Curiosity's mast camera can be used to examine possible routes and targets to the east, including rocks for the first use of the rover's hammering drill. That instrument is designed to collect samples of powder from rock interiors.
3, 2, 1. Main engine start, 0, and liftoff.
1 year ago, on November 26, 2011, NASA's Mars Science Laboratory Curiosity rover launched aboard a United Launch Alliance Atlas V rocket from Cape Canaveral Air Force Station in Florida. MSL reached the Red Planet in early August of this year.
Touchdown confirmed. We're safe on Mars.
At a site known as Gale Crater to begin its 2-year prime mission. The rover's 10 instruments are investigating whether that area of Mars could have ever sustained microbial life.
Hi, my name is Torsten Zorn. I'm Tactical Downlink Lead on the Mars Science Laboratory, and I'm coming to you with your Curiosity rover report. Since November 10th, we've been tracking a very large dust storm on Mars with Mars Reconnaissance Orbiter, Curiosity, and Opportunity. Luckily, this dust storm has abated, and even if it didn't, it would have been fine for Curiosity. It's well within its design limitations. Recently, Curiosity was able to take a beautiful high-res image of herself using the Mali handheld imager. By putting together a sequence of very complex arm motions, we were able to take dozens of images and splice them together, creating a beautiful self-portrait. After several weeks of being stationary at the Rocknest site, we began driving again on SAW 100. This marked a significant milestone on the mission as we reached about a half a kilometer of total driving distance on the surface of Mars. Currently, the left front wheel is sitting on a rock that we've dubbed Bell Island. We plan to back up off that rock to bring the rock into the ARMS workspace, and we're going to do some contact science on it with APXS and Mali. After completing our science campaign at our current location, we're going to be moving to the east to a place called Point Lake. From here, we're going to be looking for a target to perform our first ever drill on Mars. This has been your Curiosity Rover Report. Check back for further updates.
Science news from the American Geophysical Union's 2012 fall meeting in San Francisco was headlined by NASA's announcement of a new, robust, multi-year Mars program that will feature a new Red Planet rover set to launch in 2020.
While 2020 may seem a long way off, it's really not. You know, Curiosity was about a decade in the works. We have a tremendous amount of systems engineering and even spare parts left from the MSL chassis, and those are really the enabling things that allow us to do this.
The new rover will be based on the proven architecture that safely landed Curiosity on the Martian surface this summer. The 2020 mission will gather new science data about Mars and serve as the next step towards meeting President Obama's goal of sending humans to Mars in the 2030s.
Hi, I'm Ashwin Vasavada, the Deputy Project Scientist for the Mars Science Laboratory, and this is your Curiosity Rover Update. It's been a momentous week for Curiosity. We've wrapped up our scientific study of Rocknest, which also means that we've completed the checkout and first scientific use of all of our instruments on the rover, and it truly is working great. We began the Rocknest campaign by searching for a suitable drift of sandy soil using our Mastcam color cameras. We used our ChemCam laser and our APXS chemical sensor to do an initial chemical analysis of the soil, determining whether it was similar to soils that we understand from Spirit and Opportunity, and therefore safe for scooping and sending to our laboratories. We used Molly, our hand lens imager, to take close-up views of the soil to look at different particle sizes, shapes, and colors, and how they change with depth. We then scooped up the soil and analyzed it with our X-ray diffraction instrument that can identify minerals in the soil based on their unique crystal structure. But it turned out that a good amount of the material in the soil was not crystalline, but that's no problem for our other laboratory, SAM. SAM heated up the soil in an oven and measured various gases released as the soil components broke down, such as water, carbon dioxide, oxygen, and sulfur. Not surprisingly, the results show a composition that is typical of Mars soils studied at other sites, with perhaps some very simple carbon-containing molecules and perchlorate salts. We haven't yet seen any complex organic molecules, but sand isn't the best place to look. Finally, it's worth remembering that the big questions in science, whether Copernicus finding that the Earth goes around the Sun, or Darwin showing that natural selection drives biological evolution, were answered only after many measurements were taken, compared against one another, and hypotheses were proposed and tested against the data. Only then can the big picture emerge and the theory get accepted. It'll be no different for Curiosity in its mission to understand the habitability of ancient Mars at Gale Crater. There won't be any single image or measurement that'll answer everything. We're in it for the long haul. But now we know that we have a fantastic rover, a great set of tools, and a fully functional scientific payload. So let's get on exploring. This has been your Curiosity Rover Report. Please check back for more updates.
You are the STEAM heroes of tomorrow. Stay focused, dream big, anything is possible.
NASA joined forces with Discovery Education, provider of digital resources to U.S. classrooms, and entertainer will.i.am's I Am Angel Foundation to take students on a virtual field trip to Mars. Hosted by NASA Associate Administrator for Education, Leland Melvin, and Solar System Exploration Program Executive Dave Lavery, Journey to the Extreme provided an opportunity for students across the country to meet the scientists, engineers, and innovators behind NASA's Mars Curiosity rover mission.
Hi, I'm Colette Lohr, Tactical Uplink Lead on the Mars Science Laboratory mission, and this is your Curiosity Rover Report. Recently, the rover drove by an outcrop called Shaler, where we used Curiosity's chemistry and camera, or ChemCam instrument, and mast camera to look at the rock's composition and observe its layering. Then from Shaler, we drove another 50 meters or so, and we descended roughly half a meter into a location called Yellowknife Bay, making science observations along the way. The team is now searching in earnest for a suitable rock for our first drill activity after the holidays. This has been a really exciting time for the team because we've started to do what we call discovery-driven planning. And this is when we, in a sense, hand the rover keys to the science team. In the early part of any mission, much of what the rover does is pre-scripted as we kind of perform checkouts and do first-time activities. But in recent sols, or Martian days, the science team has really had more freedom to send the rover where the science takes them. These days, the team's busy preparing to preload the rover with 11 sols of activity over the course of 2 Earth days, and this is going to allow us to spend the holidays with our friends and families. This capability will come in handy when we experience solar conjunction coming up in April. This is where the sun positions itself between the Earth and Mars, and that's going to interrupt our ability to communicate with Curiosity for upwards of 2 weeks. Curiosity is expected to drive another 30 meters to a location the team has informally dubbed as Grandma's house. This is where she'll spend the holidays, acquiring a 360-degree panorama from within Yellowknife Bay. A small team will still be on hand working during this period to monitor Curiosity's health. On behalf of the Mars Science Laboratory mission, we wish you all a very happy holiday and look forward to many new adventures with Curiosity in the new year.